Hello, a warm welcome to all of you students, those who are watching this video. My name is Virup Moitra and I am a postgraduate student pursuing MSc in Mathematics with data science. Right now I am recording this video from my institution where I am studying, so for any kind of background noise or interruption, I apologize for that. In this lecture, I will discuss with you the pre-college calculus knowledge. This video, rather the coming series of videos, is basically dedicated for high school students. That is basic limit and continuity, discontinuity, differentiability, and the applications of derivatives, and so on. So today I will discuss the concept of limit and we'll discuss some problems as well. Okay, so let us start. So our first topic is that the limit, uh, the the concept of limit. So our main concerns are limits and continuity, which are important aspects of analysis in mathematics. And if you attend further classes of mathematical analysis like real analysis, complex analysis, and so on, you will relate these kind of things with those hardcore or and deep core mathematical stuff. So first we start with a preliminary discussion of limits. So next we took a closer look at the concept of limit and extend it in the direction of continuity. I want to provide a intuitive approach of limit. So let's write something. So limit and continuity. So the so first let's start with the intuitive approach of limit and then we'll derive the formal definitions of limit. Okay, so suppose there is a to understand the basic meaning of limit of a function, we begin our discussion with some specific examples. So example, like if you take the function, the suppose the function f of x equal to 3x plus 5. So the value of function at x equals to 3, so the value of function at x equals to 3, so that is if I take f of x, so if f of 3, that is so it will be what? It will be 14, right? So if we want to know the behavior of the function when x is near 3 but not equal to 3, okay, so how it could be? So this is our x. So let us make a table like this is our x, okay, and this is our fx, okay. So if I take 2.5, so if you calculate it and you will get what? So f of x, so f times f of f of 2.5 will be 3 times 2.5 plus 5. So it will be what? It will be 12.5, sorry, 12.5, right. So the function will be 12.5. Now, so now instead of 2.5, let's 2.6. So 2.6. So it will be what? It will be 12.8, right? So it will be 12.8, and now it will be, if it is 2.7, and if you calculate, use the calculator. So I am using calculator. So if we do so this is 13.1, right? So 2.8 will be 13.1, not 13.1, 2.8, 13.4, yes. And if I do so if it is 2 point something 999, it will be what? It will be 13.997, and again 2.999, it will be 13.9997. So same thing you do with 3.5. So if you take say x, and this is f of x, okay, and if you take 3.5, you will get 15.5, okay. If you take 3.4, it will be 15.2, 3.3, this will be 14.9, okay. And if we keep continuing this up to 3.001, so it will be what? 14.003, again 3.0001, so it will be 14.0003, 3.000, and one more 0, so 1, so it will be 14.4 zeros after decimal 3. So it will go like this, and what you will get, so you will get what? You will get, so if you draw a graph, okay, so let me rotate this, okay, sorry, yeah. So if I just let me set this out, okay, properly, and yeah, so if you draw a curve, or draw a graph, so you will get what? You will get a straight line here, which is 3.14, 3,14, okay. So this is 3,14, okay. So yeah, so this is 3,140, okay. And so if you do so from the table and graph, you will see that the function shows in this figure, in this whole graph. So you see that when the value of x approaches towards 3 from the left or from the right, so the value of this function approaches 40. So from the table. So from the table you can see, so from the table you can see uh, that as x, so we'll use a right arrow like this to denoting that x approaches towards something, a value. So x approaches 3 from the left, okay, from the left or from the right. The value of the function that the value of the function, that is f of x, approaches (14), right? So it appears that we can make the value of function as close as we like to 14 by taking x sufficiently close to 3. So now we express this by saying the limit of the function, okay. So it means, so will you say that the limit of the function that is this f of x as x tends to 3 is equal to 14. So to all have discussed here, we give a notations. So let me highlight this. So these things, this entire things, whatever I have just said now, will use the notation. So what will be the notation? So the notation will be like this. So the notation will be like this. So limit of the function x tends to 3, that is limit of x tends to 3. So this x tends to 3 is like is written like this. So that this is 3x plus 5, okay, which is nothing but 40. So in general we use the following definition for intuitive approach, okay. So now we will give the definition, we'll write a definition. So that is the definition. So what is the definition? So we'll write the if the function f of x, if the function fx gets arbitrarily close, arbitrarily close, then to some real value, then L as x gets sufficiently close. Okay, sufficiently close to A from both the side. Okay, so that's why I will write from either side of A, but not equal to it. Okay, but not equal to A. So we write it as so limit of f of x. Okay, so as this x tends towards A, and this will be equal to A. Okay, so and say that the limit of fx, limit of function, is equal to L as x approaches to A. So that is, we can write and say that the limit of f of x is equal to L as x approaches to A. So let me highlight this. So this. Okay, so this is important. And you can see that. So let us evaluate the value. Okay, so let me go to next page. So evaluate the value of limit x tends to 3, and this is x square minus 3 and x square plus this is x square minus 3 and this is x square yeah, x square minus 3, let's take it x square minus 3 and take it x minus 3. Great. Now here the function fx is not defined when x equals to 3. Okay, so we'll write that here fx equals to, that is x square minus 3 by x minus 3, is not defined when x equals to 3. Okay, but it doesn't matter because as per the definition of limit, we can take the values of x that are close to 3, okay, but not equal to 3. So we make a guess that this limit of x approaches 3. I repeat, I repeat that as it is not defined when x equals to 3, so it doesn't matter, because as per the definition of limit we can take the values of x that are close to 3 but not equal to 3. It's approaching towards 3, okay, so very close value. So as I have written in the previous slide, so you can see this. So I am taking a very closer value of 3, right? So I am taking x approaches towards 3 but not 3, so that's why 2.999, 2.999 and like this, okay. So that is the thing. So here it is also, so it's approaching towards 3, okay, but not exactly the 3, so it is 3.001, 3.0001, like this. So that's why I'm claiming like this, that x that are close to 3 but not equal to 3. So we can make a guess that x that is, so limit of x that is approaches to 3. So this x square minus 3 and x minus 3, and if we do so it will be limit of x plus 3 and the limit x approaches 3, so it will be 6, right? So you can see this. So if I what I just did, so I just the things I have just break it down, okay. So this is the thing actually I have done, okay. So you can see that now the thing is to define the mathematical approach of limit. So we have discussed the definition of limit with the intuitive approach. So mathematical description of limits must be based on some analytical work for deeper understanding and rigorous proof, okay. So now we'll define something which is, say, the definition this is epsilon delta approach. Now we will ask that what is epsilon delta approach. So if I write that let fx, the function, fx be a function defined, be a function defined on some open interval containing a real number c, real number c, so except possibly at c itself, okay, except possibly c at c, so then fx is said to tend is said to tend to C not tend to C, sorry, tend to a limit L as x tends to C. Okay, so if for every, so I'm going to next page. So if for all epsilon, so I'm taking a epsilon, that is this epsilon is arbitrary, so epsilon greater than 0, so no matter however small it is. Okay, so there is a corresponding number, say delta, and delta is also a positive. Okay, depends on epsilon. This epsilon such that this f of x minus L, and this can be evaluated like this fx minus L, that is evaluated, and these things, this entire quantity is lesser than epsilon whenever, that has to follow a condition, whenever 0 sorry, not 0, so this the distance between x and C, okay, that is in between 0 and the value of delta. Okay, so this definition is illustrated as per a graph which I have previously made for you, that is, so these things, so yeah, so let me adjust it. So yeah, okay, so this is my f of x. Okay, so this is my fx. Okay, so this is y equals to fx. Okay, so here I have defined, so this definition is basically based on this drawing I have made in a Cartesian coordinate. So if for a given epsilon 0, so for a given epsilon greater than 0, we can draw this horizontal line. So we can draw a horizontal line that is y equals to L plus this epsilon, and y equals to L minus epsilon. Okay, and this graph of the function, that is this fx, if the limit exists, okay, then we'll find some number, say that is this delta, that is positive delta, such that we restricting this x. So we restrict x lie in the interval of what, C minus delta and c plus delta. So you see this and this. So these are some draw this horizontal line. Okay, sorry. Okay. Yeah. So as I was saying that that if we draw this horizontal line, that is y equals to L plus epsilon and this L minus epsilon. Okay, so this things is basically drawn in this scenario, so that this for this delta positive we are restricting this x lie in this interval, so this open interval, and keep it mind that x not equal to c. Okay, so then the curve, so then the curve y equals to f of x lies between the lines y equals to L plus epsilon and y equals to L minus epsilon. You can see. So again I am repeating that for a positive epsilon there is some corresponding number I am taking, that is a delta, and this delta depends on epsilon. Okay, and such a way if we evaluate our function and we measure the distance or the how the things is getting closer and closer towards L, so whenever this condition has to be satisfied. Okay, so for a given epsilon, arbitrary epsilon, it doesn't matter that however small it is, so we can draw a horizontal line, that is y equals to L plus epsilon and y minus L minus epsilon, and we are restricting x which is lies between the interval c minus delta and c plus delta, and you can see this curve, this entire curve is lies between this y equals to L plus epsilon and y minus y equals to L minus epsilon. Okay, now so if we solve some problems, so how it could be or how things get be look like. So let me write a problem for you so that you can understand or digest the meaning of the epsilon delta approach of definitions of limit. Okay, so yeah, so let me write it down. Say so if I say prove that limit, okay, prove that limit as x approaches to z in 2 and the function is 3x minus 5 which is equals to 1. So how will prove that? I will write the proof in a very rigorous manner. So I am showing you that. So first, so let solution. So let epsilon be a given positive number. So, or you can write let epsilon greater than 0. Okay, so that is that is what mean that epsilon be a given positive number, right? So according to epsilon delta definition, we will write that with c equals to 2, right, and L equals to 1. So if we compare these things with the epsilon delta approach definitions 1, so we can find a number. So we can find a number that is delta, which is definitely positive, and it depends on what, epsilon, such that so we'll write this 3x minus 5 minus 1. So let me, so 3x minus 5, okay, and this is lesser than epsilon whenever this condition will follow. So as per the epsilon delta approach, so we have considered that there exists epsilon which is a positive number, which is given a positive number obviously, and according to this definition we consider that this so these things we have considered, that is c equals to 2 and the L which is 1. Okay, now we can define a number such a way that this epsilon delta definition be constructed, and whenever it will construct, when it follows this definition or the this conditions, I will say. Now next you are willing to write next part of the proof, or approaching towards proof. So this is if and I'm sorry so this is if and only if, so if and only if 3x minus 5 minus 1, okay, so this is evaluated 3x minus 6, and if I take the 3 outer of this modulus, so 3x minus 2, 3 times x minus 2, so therefore we have 3 times x minus 2, which is lesser than this epsilon whenever this condition will be satisfied. Okay, yeah, so we'll choose a delta. So how I should choose this delta? So so delta would be like, so if I take so we choose, so if we choose delta like this way. Okay, so that is what? So if I, in the next step, if I just write it down here, so you think like this. Okay, so you just think like this, that in the next line I have just write this epsilon by 3. So this epsilon by 3 is delta. So delta is like this, and that's why I am saying this delta is depending on epsilon, right? So we'll write like this way. Okay, not like this way, this is not the proper way to write. So we choose, so if we choose delta equals to epsilon over 3, then this 3x minus 5 minus 1 and this epsilon whenever this 0 lesser than will satisfy, and it will return this like this way. Okay, so therefore by definition, so we'll write therefore by definition of limit we have limit of 3x minus 5 limit which approaches towards 2 3x minus 5 equals to 1, and hence it is proved. Hence it is proved, and we'll write the problem in this manner. Okay, so before we close this section, we give a very important result in limits, that it is called the uniqueness theorem. So it says that the limit of a function is unique if it exists. Okay, so the proposition is like this. So let me write proposition. So what is the proposition? That is, so if I write, so the limit of a function is unique if it exists. Okay, so we'll prove this. How we'll prove this? So let us see. So we always need to prove such things. So I will write the proof. Suppose that if there is a function and this a maps to the real number, and there exists a c which is belonging to this real number is an accumulation point, okay, is an accumulation point, right? So of what? A is subset of this R, okay, that is what, that is, so if we assume that, so assume that this limit x tending to c, okay, f of x equals to L1 and limit x tending to c f of x equals to L2, right? Now where L1 and L2 belonging to this real number, so for every epsilon positive there exists a delta 1 delta 2, right? So for every epsilon positive there exist delta 1 and delta 2 which is positive, okay. Now such way that this condition should follow, so which is what, x minus c is evaluated in between 0 and delta 1 and this x minus c, it is delta 2 and 0 and delta 2. So and x belongs to a, which implies that f of x minus L1 which is lesser than some epsilon, that is we take epsilon over 2. So see how I am deriving, so let me clarify these things. So as it is said that limit of a function is unique, so I am as it is the function it is saying, so that's why I am defining a function and there is a set A and this A maps to the real number set, and I am defining a C, arbitrary C, which is also the part of this real number. So as we are talking to limit of function, so that's why it is clear that this setup is already known to us, okay. So this setup is already known to us. So as it is known to us, as it is defined, so we can we can write it in a reverse manner, right? So that's why we are writing in this fashion, okay. And similarly x belongs to A, which implies that this f of x is L2, okay, which is also lesser than epsilon over 2. So we'll take the minimum, we'll try to figure, not maximum. Why maximum? So as we are trying to a very closer towards this so as the limit thing is unique and we are trying to figure it out, the closer, more as much as closer of this function, so we'll take the delta as minimum, okay. So as it is different delta, we'll take the minimum delta, so that this previous condition follow, and as this condition follow, as we can see these things from, we can derive such things, or if we compare things like this way. So, and we know this delta is depends on epsilon. Okay, so we have to take this delta in somewhat sense that it's a minimum, as much as minimum, okay, in between two different delta. Okay, so that's a take, let delta is equals to minimum of delta 1 and delta 2, okay, which is definitely has to be positive. So since C is an accumulation point, okay, then C is our accumulation point, okay. So that's why accumulation point of A, okay, so that's why there exists, so like there exists X belongs to A such that this X minus C is evaluated like this as we defined previously, and it follows that this L1, sorry, so this L1 minus L2, okay, so this L2, this is evaluated in between. So if we adjust the things like this way and apply the triangle inequality, so you will find that this L1 minus f of x, okay, and f of x minus L2, okay, so this is then this epsilon, since this holds, okay, since this holds for arbitrary epsilon positive, so we must have this L1 equals to L2, okay. So this is what we want to prove, that the unique, so the limit of a function is unique. As it is unique, so that's why there doesn't exist two different limits, okay, so it follows it approaches towards one limit only. So that is the thing we want to mean. So if you note that, so if you carefully note that the things that this proof, so this proof we have we used to requirement in the definition of limit, that this small c is an accumulation point of A. So the limit definition would be vacuous if it was applied to a non-accumulation point, okay, and in that case every this L, which is a real number, would be a limit, okay. So we can refresh, not refresh I want to mean, so So if this epsilon delta definition is rephrased in things like the limits in terms of neighborhood, okay, so that's what we mean in this defining this epsilon delta approach here, the neighborhood concept and things. So if you are aware with the concept of neighborhood, so it will be helpful. If it is not, let me know in the comment box so that I can help you to understand that what is the concept of neighborhood or what does it mean to us. Okay. So sometimes we see that some limits are best calculated by first finding the left hand right hand limits. Okay. So in this next we this epsilon delta definition of left and right handed limits. Okay. So we will write the left hand and right hand limits. So left hand, and right hand limits. Okay. So if I write so if f be a function, let f be a function, so function defined obviously in a open interval, defined in an open interval, okay, and containing C obviously, C. So then fx has a limit L from the left at C, the left at C. Okay. So if for a given positive number, so if for a given positive number, this epsilon is greater than 0 and there exists a positive delta obviously, okay, and there exists a delta positive, okay, such that will follow such a notation, that is f of x, this f of x is evaluated in this whenever c minus this delta is lesser than x lesser than c. Okay. So symbolically if we write this, so symbolically it is written in this limit of f of x, okay, and if we take x c minus, and this will be limit of left hand side, okay. So let me write it as left hand limits, so left hand limits, so left hand limit. Okay. Now similarly we will define right hand limit. How right hand so how this right hand limit could be written as. So same definition. So you try to define this, you have to define these things first. Okay, that is uh, so you have to define these things. So how you will define? So I'm saying, so verbally I'm saying, I'm not writing. So let, if be a function, again same things you will write. If be a function defined in an open interval which is contained in C. Okay, the same thing, same you will write, but what changes you will do, or how the changes will look like. Okay, so we'll take the right hand limit. So we'll take, that is, this is C minus delta. So instead of that we'll write C plus delta. Okay, so we'll change that thing. So f of x, this will be evaluated following this condition, that C is lesser than x, and as it is right hand side, so C plus delta. So symbolically that this limit x approaches towards the positive, so this is so this is what we define. So in definition of limit, we know that limit exists if and only if both the one-sided limits exist and are equal. Okay, so we'll write that. So from the definition of limit, so from the definition of limit, so the limit exists, we'll write that limit exists if and only if, so this is the writing of if and only if both one-sided limits, both one-sided limits exist and they have to be equal. Exist and equal. Okay, so we'll write a theorem like this. So the theorem, so we write this theorem like this way, that limit, okay, this limit x approaches towards C, f of x, which is L, if, so this is the symbolic notations representation of these entire things. Okay, so if and only if limit of both sided exist. Okay, so limit of both sided exist, and which is what so we'll write that limit x goes to C f of x equals to L minus equals to L equals to limit of x approaches towards C positive f of x equals to L positive. And this is what we write limit of, so yes, yeah, this is what we write. Okay, so so there are some algebras on limits. Okay, algebras of limits. Suppose so there are a lot of limit algebras. So how these things written? So you see. So from any book you will find this, or if you just do some researches on your own, so you will find this. So suppose, so we'll write this. Suppose if alpha is a constant, okay, so for alpha constant, if, okay, limit of x approaches to c, f of x equals to L, so L1 I am writing, and limit, okay, so again I am writing limit at x approaches to c, okay, so c, so this gx will equals to L2, okay, then this things 1, so we write this 1 equals to I'm sorry, so we can write this limit of f of x, which is g of x, okay, which is L1 plus L2, okay. So this is I should write it plus minus, so both can be possible, so I should write this in this manner. So this is plus minus, and this also plus minus L2. So if it and so next thing is limit, which is x tends to c, f of x and g of x will be L1 times L2, okay, and if I multiply some constant with my limit, so what it would be? So if I write limit of x tends to c some alpha times this f of x, okay, so it will be some alpha times limit of x tends to c f of x, okay, and it will be alpha times L1, okay. So this is the things. And if suppose, so in the next page I will write say if gx, there's a function, the limits, there's a function gx, and if I take the limit of this, that is so gx, which is L2 and which is not equal to 0, then we can write that limit of x approaches to c, f of x over g of x is written as limit of x tends to c, f of x, I'm sorry, yes, so limit of x tends to c, g of x, which is nothing but L1 over L2, okay. So similarly, if you take the we can say some power law things. So if limit x approaches to c, so this was the third, this is the fourth, and this is the fifth. So x approaches to c, so if I take f of x to the power say n, so this will be ln to the power n. So where this n is positive, and if I take the square root, I mean the nth root of f of x, okay, and if I take the limit of this, so it will be square root nth root. So nth root is something like 1 by n, right? So this is what is happening. So that's why we are writing this way. Okay. So for n positive. Okay. Yeah. So now, so these are the main fundamental things for understanding limits. So in a next session, we'll define a very important things, which is say the squeeze theorem or the sandwich theorem, and the laws of infinite limits and limit of infinity, and we'll solve some problems which is associated with the epsilon delta definitions, and solve more problems, and we'll solve problems on sandwich theorem. We'll see some graphs. So next session will be a bit not like this much longer. So next session will be a bit shorter, like 30 minutes or 40 minutes for on problem solving and discussing some theorems and consequences with limits. And then we will move on to the idea of continuity, and before that I will try to derive or make you understand that what is the intuitive understanding of continuity, what is basically the continuous function mean to us. Okay, and we'll do the continuity and discontinuity, solve some problems and consequences, and if there is necessary theorems, I will definitely elaborate that in a very layman way, and then we'll derive more formal definitions and for rigorous proofs and rigorous problem solving. Okay, so for this time, okay, goodbye. I'm ending this session here. Okay.